All right, so I'm going to talk about combustion analysis here, and this is really kind of a culmination of stoichiometry and empirical molecular formulas, and that this is like a hard problem that incorporates a lot of things. This is great for problem solving, great for maybe an extra credit question or something on the exam, but this is combustion analysis. So we have talked about combustion reactions. A combustion reaction is when you have some type of what's called a hydrocarbon. So it's got carbon, hydrogen, and sometimes oxygen. Reacts with oxygen, right? If you burn something, you get oxygen in the air to make CO2 and H2O. Okay, so it's C something, H something, O maybe something, reacts with O2 to make CO2 and H2O. So what we do is if you have a compound and we don't know what it is, we're going to do an analysis. And so we're going to combust or react it with oxygen to find its original formula. So was it C2H5O1? I don't know. That's what we're going to figure out what these subscripts X, Y, and Z are for this formula. Okay, so it looks like this. We take our sample, we burn it with oxygen because you have to have oxygen to burn, and then we absorb all of the H2O and we absorb all of the CO2 so we can figure out, well, how much CO2 and how much H2O did it make? And then we can find what its original formula was. We can kind of work backwards. So like I said, this is kind of a little bit of stoichiometry and empirical molecular formulas. So how do I do this? First thing you have to do is we have to figure out how much carbon, hydrogen, and oxygen were present in the original sample, because that's the thing I'm trying to find the formula of, is the original thing that you reacted. Okay, so how do I do that? You use stoichiometry to find those masses, because then we can do the empirical formula rules. So the carbon, all of the carbon from this reaction would have gone into the CO2. All of the hydrogen from this compound would have gone into the water. Now the oxygen could have been from this oxygen, so you want to do oxygen last, okay? So the carbon would have gone into carbon dioxide, the hydrogen would have gone into H2O. So this is what you're going to do. You're going to figure out how much carbon from the CO2. How much carbon did you make? How much hydrogen from the H2O? How much hydrogen was there from the water? And then whatever was left was from the oxygen. Then you have the amounts of carbon, hydrogen, and oxygen that came from your original sample. You can then find your empirical formula using the convert moles, divide by the smallest one, and find that, like, so subscripts. All right. So I'm going to walk through example number 12, and I'm going to do it with you. All right. So I did combustion. So I know this is combustion analysis of 0.8233 grams of a sample. Okay. So this is my unknown sample. I don't know what it is. It contains only carbon, hydrogen, and oxygen. So it's C something, H something, O something. Okay. I need to know those numbers. It produced this much carbon dioxide and this much water. Remember I said that all of the carbon in here is from the carbon in my sample. All of the hydrogen in here is from the hydrogen in my sample, and the oxygen is the rest. So what is the empirical formula of this compound? So first we have to do stoichiometry with this guy and this guy. I do the reaction backwards to figure out how much carbon. All right, so I got 2.445 grams of CO2 over 1. Molar mass of carbon dioxide is 44 grams of CO2 per 1 mole of CO2. Now I need just the carbon part. So this is kind of like a component within problem, just the carbon part, but 1 mole of CO2 has 1 mole of carbon. Okay, so that will tell me how many moles of carbon were in my original thing. Okay, I'm gonna do the same thing here with water. 0.600 grams of H2O over 1. 18 grams is the molar mass of water, or 1 mole, times, of H2O. But 1 mole of H2O actually has 2 moles of just hydrogen. So if I want to know just the hydrogen part, I do have to multiply by 2. Okay, so I'm going to do that math really quick. Okay, so that means that originally there were 0.05568 moles of carbon and 0.06667 moles of hydrogen. Okay, so once I have these amounts, I've got this many moles of carbon, and I know I already filled in the rest, and this many moles of hydrogen. Well, I know the rest was oxygen because it's carbon, hydrogen, and oxygen. So in order to figure out how much oxygen there was, well, the whole compound started as 0.8233 grams. How much of that was oxygen? Well, if I subtract out how much was carbon and how much was hydrogen, I would be left with oxygen. So the first thing I did is, because you can't subtract moles from grams, you have to convert these to moles. So I would do this times 12.01 grams of carbon, and I get 0.663 or 737 grams of carbon. Then we're from that original sample, and 0.06667 moles of hydrogen times 1.01, that's hydrogen's molar mass, is this many grams of hydrogen. So that means that of my beginning 0.8233 grams, this much of it was carbon and this much of it was hydrogen, the rest was oxygen. So then if you go down here, I did my original sample and I subtracted the carbon part that I had just calculated and the hydrogen part that I had just calculated. And that means that there was this much oxygen, 0.0885947 grams of oxygen. Okay, so I've got the amounts of carbon, hydrogen, oxygen. Now I can go to the next part, which is using your empirical molecular formulas methods from before. So I don't have percentages though, I have grams. I have grams of this, and grams of this. Well, then that's how many grams you have. Go ahead and convert them to moles and then divide by the smallest. Well, lucky for you, we already have moles of carbon. You don't have to like recalculate it. We already have moles of hydrogen. I just had to calculate moles of oxygen. So I did oxygen divided by its molar mass, which is 16, which is this. So I have this many moles of carbon, this many moles of hydrogen, and this many moles of oxygen. So I divide them all three by the smallest value, which was oxygen, 0.0553717. So I have one oxygen. To this divided by this is like 10.01 or something. I get 10. And this divided by this is about 12. So it's 10 carbons to every 12 hydrogens to every 1 oxygen. So this would be my empirical formula. So again, this problem kind of encompasses everything that we've done in this unit. It's very difficult. If you need help, please don't hesitate to reach out.